today I want to talk about Bodie plots again, and this time hopefully it won't suck so hard and be so confusing. So I have gone through and actually written down notes and all that kind of good stuff, and actually put thought into how I'm going to approach this. So hopefully things will turn out significantly better than they did on Monday when we introduced. So the first thing that I'm going to start with is a constant transfer function. So effectively, let's look at an example where arbitrarily h of s is some constant value k, where this would be representative of a circuit effectively containing only resistors. Okay. So still don't know why this computer is doing this today. Our frequency response plot. So up here, we're going to have 20 log h of s. And on this axis, we're going to have s. I'm just arbitrarily going to call this 10 to the negative 1, 10 to the 0, 10 to the 1, and so forth. So what should we see for a constant? Well, if I put literally 20 log of k into this expression, I'm just going to get a constant value that is arbitrarily here. So constant across all frequencies. Okay. So if we ever have a transfer function that is just a constant, it does not depend on s, our magnitude response is simply just that number in a decibel scale. Okay. Another part of the Bodie plot might be to look at how the phase angle varies with time. Right? So let me scroll down here slightly. So this would be theta as a function of s. I'm going to put those same values, 10 to the minus 1, 10 to the 0, 10 to the 1, and so forth. This is our s-axis. Let's make this correspond to negative 90, this correspond to minus 180. Actually, those should be positive because that's the positive axis. My apologies. Negative 180 down here. So for a system with a transfer function that is a constant, do we expect to see any phase change as a function of frequency? Absolutely not. So our phase angle would literally just be, that is not what I meant to do. That is even less what I meant to do. There we go. A constant value of 0 degrees over the entire frequency spectrum. All right. So this is the easiest, dumbest possible case, effectively, but it is a fundamental building block of what we're going to be doing today, or at least the way that I'm choosing to approach it. All right, so are we all on board with what the transfer function, excuse me, what the frequency response of a transfer function that is a constant value looks like? On the magnitude side of things, it is just going to be 20 times the log of that constant value so that we're in decibel scale. And for our phase angle, it is just 0 degrees. Okay. So now let's look at a system that has a pole at the origin. So this could be something as simple as just 1 over s. So what I want us to do is effectively build a simple table here and kind of figure out what's going to go on, and then we'll put that specifically in graph form, right? So let's say that I have S here, and then H of S here, and then H of S measured in decibels here, or 20 log of H of S. So let's say that S were 0.1. What would H of S be? 10. What would 20 log of H of S be? 20. What if S were 1? What would H of S be? 1. What's 20 log of 1? 0 decibels. What if S were 10? What would H of S be? 0.1. What would 20 log of H of S be? Negative 20 decibels. So it should be fairly obvious that we have a linear relationship going on right here. So if I were to plot this, here I have 20 log H of S. Here's S. Let's put 10 to the 0 here, 10 to the minus 1, 10 to the minus 2, 10 to the positive 1, 10 to the positive 2. This would be, oops, stop erasing things I don't want to erase. So let's call this 20 dB, 40 dB, 0 dB, negative 20, negative 40, like so, based on the plots. So for S is equal to 0.1, that would be right here. Our value was 20. For S is equal to 1, our value was 0 decibels. For S is equal to 10, our value was negative 20 decibels. And I'm just going to connect these dots. Like so. We can see very easily that our slope is negative 20 decibels per decade, where a decade is defined to be this distance on the x-axis. So going from 10 to the minus 1 to 10 to the 0 is a decade, 10 to the 0 to 10 to the positive 1 is a decade, and so on and so forth. So we can see very explicitly that when we have a pole at the origin, our transfer function here, excuse me, the frequency response of our transfer function crosses the horizontal axis at S is equal to 1, or 10 to the 0, and that we have a slope of negative 20 decibels per decade. Okay. So what should our phase response be? Well, this is a little bit harder, right? So let's scroll down here and let's kind of think about things really quickly. So I have the following function. H of S is equal to 1 over S. These transfer functions are valid for steady state conditions. So what I'm going to do is I'm going to substitute in the relationship. So let S equal to 0 plus j omega. Effectively, all this means is that we're assuming that our system is operating at sinusoidal steady state where the frequency is what matters and the transient condition, so the exponentially decaying part, has died out. So from that, I would simply have 1 over j omega, which is the same thing as negative j times 1 over omega. My angle as a function of S is now effectively my angle as a function of omega. Well, if I have a negative j, what's my angle? Negative 90 degrees, constant value. Absolutely right. Negative 90 degrees for all frequencies. So my phase response (180, 90, 0, minus 90). I guess realistically, I don't need to go any further than that. And realistically, I would line up my frequencies to be the exact same spot. So let me just put 10 to the 0 here and work off of that. 10 to the negative 1, 10 to the minus 2, 10 to the positive 1, 10 to the positive 2, and so forth. We would see that our phase angle is simply negative 90 degrees across all frequencies whenever we have a pole at the origin. Yes, sir. All right. So let me go a little bit further here. Right on my complex plane, the number negative j by itself has a phase angle of negative 90 degrees, right? And then I'm just scaling that by a factor of 1 over omega. So I get a constant phase angle of negative 90 degrees. When we do a 0 at the origin in a moment, we'll see that we have a constant phase angle of positive 90 degrees for that particular case. All right, so this is how a pole at the origin behaves. So now let's expand on this slightly. Okay. So let's look at a second example. I went a little bit too far. So let's say that h of s were equal to 10 over s squared. My response, so my frequency response, is going to be 20 times the log of 10 over s squared, which is the exact same thing as 20 times the log of 1 over s plus 20 times the log of 1 over s plus 20 times the log of 10 due to the properties of logarithmic functions. So effectively, if I want to determine the frequency response for this thing, It is just the frequency response of these three individual parts added together, literally added together point by point, okay? So let's look at our magnitude response over here on the left. So let's put 10 to the 0 here. So this would be 10 to the -1. This would be 10 to the +1, like so. And I want to do this part first. Let's do it in blue, okay? So what did this look like? Well, we had a value of 0 decibels at 10 to the 0. And then we know that we had a slope of -20 decibels per decade. So let me explicitly do this here. So this is +20 dB, 40 dB, -20 dB, -40 dB, like so. So this is what that first part looks like. The second part is identical. So I'm just going to put that right here alongside of it. Before we do the next part, let's think about what would happen if we added those two things together, point by point. So at this point where S is equal to 1, we just have 0 decibels plus 0 decibels. So we're still going to intersect at that specific point, right? At this point, or this value of S, or 0.1, we have 20 decibels plus 20 decibels, so that would look like 40 dB there. Down here at this point for 10 to the +1, we have -20 decibels plus -20 decibels, so that would be -40 decibels. So because we have these two things added together, we're going to see a slope of -40 decibels. Another way to think about that would be these two guys added together is just 2 times 20 log of 1 over S. So if the characteristic of the frequency response of 1 over S is a slope of -20 decibels per decade, twice that would be a slope of -40 decibels per decade. So it's the exact same thing. Now, what's this 20 log 10 thing going to look like? A constant value of 20 decibels. So adding all of these things together, let's do it kind of like this. Let me do this thing in pink first, right? So if I add my blue response and my red response to each other, I would have this line right here where I have a slope of -40 decibels per decade. When I add this constant term, all I'm doing is shifting the level up to there, right? So I'm shifting up to this point. So that's where it crosses. And putting all of this together, the gray curve is what my actual frequency response of the entire system looks like, right? So this is where I have my 20 log of H of S is my gray curve. So I've literally just added these three constituent components, added them together point by point, right? So right here, I have 20 decibels plus 20 decibels plus 20 decibels. So realistically, this would be up here at 60. At this point, I have 0 decibels plus 0 decibels plus 20 decibels is 20 decibels. For right here, I have 20 decibels, negative 20 decibels, negative 20 decibels. So I hit negative 20 decibels. For 10 to the 2, which would be out over here, I would have 20 decibels plus negative 40 dB plus negative 40 dB. So that would look like negative 60 dB when I come out to around here. So it's all just literally adding these parts together point by point to come up with the total response. Okay. What's great about this is that it's going to work literally the exact same way for my phase angle. So here's 10 to the 0, 10 to the minus 1, 10 to the positive 1, and so forth. So for my blue bit, I know that my angle was negative 90 degrees. Let me write negative 90 down here. The red bit was also negative 90 degrees. The orange bit was 0. So adding all of this together, I get a constant phase angle of negative 180 degrees. Literally also just adding the angles together point by point across the entire frequency spectrum. Any questions thus far? Does this make more sense than the bullshit that I was throwing at you on Monday? I hope the answer to that is yes. Okay, good deal. So now let's look at a 0 at the origin. So our transfer function in this case would just be S, but I'm going to be lazy and put it in terms of things that I already know. So I'm going to look at S as 1 over S, because I know what the transfer function of 1 over S looks like, and I know how logarithm works. So 20 log of h of s in this case is going to be 20 log of 1 minus 20 log of 1 over s. So my frequency response, let's make this 10 to the 0, 10 to the minus 1, 10 to the minus 2, 10 to the positive 1, 10 to the positive 2, and so forth. Twenty log of 1 is just a constant 0 dB. 20 log of 1 over s is just this line. Negative means that I'm just going to wind up flipping this line about the horizontal axis. So this line in blue is what I get when I take the red line minus the blue line. So out here, 0 minus 40 decibels could give me negative 40 decibels. 0 minus 20 decibels would give me negative 20 decibels, and so on and so forth across the whole thing. And let me explicitly write the dB stuff on the left-hand side, right? So here's 40. 20, 0, negative 20, negative 40, and so on. What should our phase angle look like? 0 minus negative 90 is positive 90. So we had 0 across all frequencies. We had negative 90 across all frequencies. Red minus blue, because that's what our logarithmic operation tells us to do, gives us this constant value of positive 90 degrees. Or let me explicitly say this is plus 90, 0, and negative 90 degrees. So I'm taking the lazy man's approach much like I did to the Laplace transform, and once I figure out how a couple of things work, I'm just going to use that to build everything else out. So, you have a question? So let's literally do this point by point. Okay, so at this particular point, I have 0 decibels, which is my red curve, minus 40 decibels, giving me negative 40 decibels. 0 minus 20 decibels gives me negative 20 decibels. 0 minus 0 is 0. 0 minus negative 20 is positive 20, and so on and so forth. Another way to think about it, though, would be a negative sign here is just going to flip the slope, right? So if the characteristic of the frequency response for 20 log of 1 over s is 20 decibels per, or negative 20 decibels per decade, when I multiply that by negative 1, it's going to look like positive 20 decibels per decade, which is exactly what I'm observing here. So just for shits and giggles, let's go ahead and actually write that down too. Okay, any further questions on poles and zeros at the origin? All right. So now let's look at what is called a simple pole. So let's start with something ridiculously simple. 1 over 1 plus s. So this is kind of our normalized case. And once we figure out how this thing works, we'll be able to play around with what happens if our pole frequency isn't just 1. Okay. So let's build a table, much like we did a couple of minutes ago. Okay. So I'm going to have S, H of S, and then 20 log of h of s. Okay. So let's start with s is equal to 0.01, 1 over 100. Okay. So if I put 0.01 into my expression for h of s, I will find that I have 1 over 101 over 100, which is just 100 over 101. So let me write that down. And in decibels, this is negative 0.086 dB, which I'm going to be lazy and call about 0 decibels. For 0.1 as my value of s, I wind up getting 10 over 11, which is negative 0.828 decibels. And once again, I'm going to be lazy, and I'm going to say that this is approximately 0 dB. So I'm at 1, what? It does round up to 1, but when we're looking at things, I'll get to that in a second. That's why I'm making a specific point to give you the actual value, and then I'm going to say, yeah, it's about that. Okay. When s is equal to 1, I have 1/2. 1/2 in decibels is negative 6.021 dB. We'll get to there in a minute. Okay. When s is equal to 10, I have 1 over 11. And that comes out to be negative 20.828 decibels. So approximately negative 20 dB. When s is equal to 100, I have 1 over 101, which comes out to be negative 40.086 dB, is approximately negative 40 decibels. So, in summary, I can see that for h of s is approximately equal to 1, for s is much less than 1, and h of s is approximately equal to 1 over s for s that is greater than 1. So I'm going to put these two things together. Right? So here's 10 to the 0, 10 to the minus 1, 10 to the minus 2, 10 to the positive 1, 10 to the positive 2. Here's s. Here's 20 log h of s. So what does h of s is equal to 1 look like? 0 decibels. Okay. So I'm just going to put a dashed line here. At 0 dB. What does h of s for 1 over s look like? We cross the horizontal axis at s is equal to 1. We have a slope of negative 20 decibels per decade. Putting these two things together, let me do this in pink. This is our approximation. So we have zero dB for S less than 1, and then we have a slope of negative 20 decibels per decade for S greater than 1. And this is a great approximation as long as we're not close to 1, right? Close to 1 is where things get a little bit wonky. So this is an asymptotic approximation, and this is how a hand-drawn Bode plot is made. What does it really look like? Mr. Finch, I'm glad you asked earlier, as you pointed out that I could round that a slightly different way. Would be something like this. So it's literally just introduced that little bit of curve so that we don't have the two lines just butted against each other at that odd angle. But for most purposes, the asymptotic approximation is good enough. All right. Let's talk phase angle. So if I have h of s is equal to 1 over 1 plus s, that is going to be 1 over 1 plus j omega at steady state. And this gives me a ratio of rectangular form complex numbers, and I don't like that, so I just want a rectangular form complex number. So I'm going to multiply this by 1 minus j omega over 1 minus j omega, giving me 1 over 1 plus omega squared minus j times omega over 1 plus omega squared. Theta of s will be theta of omega, which is just the arc tangent of the imaginary part of this thing. So that'll be negative omega divided by the real part, which is 1, where I'm taking into account that the denominators of both of these things are the same thing, so they're going to wind up canceling each other out when I do that division, so I didn't bother putting them there to begin with. So I have the arc tangent of negative omega. So, because I can't do an arc tangent to save my life by myself, I have Desmos up. So if I do, let's see, arctan of negative x. Now I'm going to go over here to my settings. I need to get this zoom thing out of the damn way. And I want to go to more options, and let's make the x-axis logarithmic. Let's also put things in degrees. And let's make our y-axis go from negative 180 to positive 180. And get this out of the way. Okay. So if we look at this graph, we can see that exactly at our pole frequency, which in this case is 1, we have a value, phase angle of 45 degrees. And to prove that to you, just overshot it. Son of a bitch. Well, you guys can see it. 1 corresponds to negative 45 degrees. So at our specific pole frequency, the angle is negative 45 degrees. About a decade earlier than that is when it starts to transition And about a decade later than that is when it's settling to its final value of 90 degrees. So that is the approximation that we are going to make for the phase response. At 0.1 of whatever our pole frequency is, it was at 0 decimal or 0 degrees. And at 10 times whatever our pole frequency was, it was at 90 degrees. So plotting this out, ten to the 0, 10 to the -1, 10 to the -2, 10 to the +1, 10 to the +2, and so forth. This is 0 minus 90, actually, 45 minus 90. There we go. We know that at this specific point, our phase angle was -45 degrees. So we have 0 degrees until we hit this point, straight line until we hit this point, and then constant value of 90 degrees. And realistically, it's a bit smoother of a transition than that, but this will be good enough for our intents and purposes for a hand-drawn Bode plot. Okay. What do you think would happen? Actually, let me write this down explicitly here. So what we have observed is 0 degrees for S less than 0.1 omega p, and 90 degrees for S greater than 10 times our pole frequency of omega p. Yes. So S is equal to sigma plus j omega. That is literally the definition of S for the Laplace transform. We are saying that the real part of S is 0, specifically so that we're looking at our systems at a steady state condition. So effectively sinusoidal steady state. So with the sigma part being 0, it means that all of our exponential decay has died out. So what would happen if we had a repeated pole? What would happen if I added this to another version of this? The transition would start here still, the transition would end here still, but it would go down to negative 180 degrees. Because negative 90 plus negative 90 is negative 180 degrees. So for every order of the repeated pole, we can actually say it's n times 90 degrees for however many times that pole is repeated. And the exact same thing would actually happen up here in the magnitude response. It would be n times negative 20 decibels for how many times the pole is repeated. All right, so now let's mess with this ever so slightly and see what happens if we don't use a pole frequency of 1. Let's do it down here. So what if h of s were equal to 1 over 1 plus s over 100, where this 100 is just standing in, let me put this as a generic pole frequency, omega p. Well, h of s is still going to be approximately 1 for s that is much smaller than 100 for our pole frequency. and h of s will be equal to 100 over s, or let me put it in blue, omega p over s, or s is much larger than 100. So what is that going to do to our response? It's just going to shift it to s is equal to omega p, right? So effectively, in this case, we put 10 to the 2 here, 10 to the 1 here, 10 to the 0 here, 10 to the 3, 10 to the 4, etc. 20, 40, negative 20, negative 40, and so forth. We have this is the part corresponding to h of s is equal to 1. This is just going to be whatever 1 over s looks like. And then we add 20 decibels to it, or 40 decibels to it, because we're at 100. So at 10 to the 0, it should start at 40. And then putting this together, we have this. So all that has happened is our response looks like 0 dB for S is less than our pole frequency. And then we have a slope of negative 20 decibels per decade for S is greater than whatever our pole frequency is. What do you think is going to happen to our phase response? It's just going to be shifted as well. Literally nothing changes except where it crosses the 0 axis effectively. All right. So now let's talk about a simple 0. Let's start by looking at a transfer function where h of s is equal to just 1 plus s. So here's s, h of s, and then 20 log h of s. So let's start at 0.01. We would have 1.01, and that would be positive 0.086 decibels, which is approximately 0 dB. For s is equal to 0.1, we'd have 1.1, which is 0.828 decibels. Again, approximately 0 dB. For s is equal to 1, we would just have 2. So that would be positive 6.02 whatever decibels. For 10, we would have 11. So that would look like 20.828 decibels, or approximately 20 dB. And for s is equal to 100, we would have 101, or 40.086 dB, which is approximately 40 dB. So in general, we can say that this transfer function looks like 1, or S is much less than 1, and it looks like S for S much greater than 1. Putting these together, we would have the following curves. So this is, we have a straight line at 0 decibels for the first part. And then we know that for just a transfer function of S, we should have a line that crosses the horizontal axis at S is equal to 1 with a slope of positive 40 decibels per decade. And then putting them together, we have something that looks like that. This is literally just the exact same thing as negative of what we saw with our pole. Because we could have just as easily written this as 1 over 1 plus S. So much like we did earlier, we would simply just flip it around the horizontal axis and we get the exact same response. For our phase response, this is going to be pretty trivial because we don't have to do any fancy math whatsoever. H of S is equal to 1 plus S would be equal to 1 plus J omega. So our phase angle would be the arc tangent of positive omega over 1. Which means for a logarithmic plot like this, let's make this positive 45, positive 90 degrees. We are going to have a phase angle of 0 until we get to about 1/10 of whatever our 0 frequency is. At 10 times our 0 frequency, we should see that we have shifted up to 90 degrees, and we just connect the dots. This is our approximation of the phase response for a simple 0. What do you guys think would happen if our 0 frequency weren't at S equal to 1? We would just shift the graphs. Okay. So any questions before we work an example and wrap up for the day? Yes, sir. So remember from literally circuits 1 that a rectangular form complex number A is equal to A plus JB can be expressed as a polar form complex number. A is the magnitude of A, angle theta A, where the magnitude of A is equal to A squared plus B squared square root of the whole thing. And theta A is the tangent of the real part, excuse me, the inverse tangent of the imaginary part of A over the real part of A. So all we're doing that's different is saying now this depends on frequency. That's it. All right, any other questions? You're whispering, I don't hear any questions. All right. So let's put this jibber jabber together and work an example. So let's say that H of S were 10 times S plus 1 times 1 plus S over 100 divided by 1 plus S over 0.1 times 1 plus S over 1,000. H of S in decibels would then be 20 times the log of 10 plus 20 times the log of S plus 1 plus 20 times the log of 1 plus S over 100 plus 20 times the log of 1 over S plus, excuse me, 1 plus S over 0.1 plus 20 times the log of 1 over 1 plus S over 1,000. Yes. Nope. I see. So these are whole responses. These are zero responses. This is a constant response. Does not have any negative signs the way that I have purposefully chosen to express this. Let's make us a pretty little graph here. So here is 20 log H of S. We have lots of frequency stuff going on, so I'm just going to make this pretty wide. Let's put 10 to the 0 right here, 10 to the minus 1 here, 10 to the minus 2 here, 10 to the minus 3 here, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. Here's S. Let's make this positive 20 decibels, 40 decibels, negative 20, negative 40. So in orange, I'm going to do my 20 log of 10, which is just a constant value of 20 decibels. Like so. In this bright green color, let's do 20 log of S plus 1, right? So 20 log of S plus 1 is going to look like 0 decibels until we get to S is equal to 1. And then we should have a slope of positive 20 decibels per decade. We'll leave it there. Let's do this guy in this light blue color. So we should have 0 decibels until we hit S is equal to 100. And then we should have a slope of positive 20 decibels per decade, like so. Let's do this light purple bit for this part. And I just accidentally erased 0.1 there somehow. 0.1 purple bit. So we're going to have 0 decibels until we hit 10 to the minus 1. And then we're going to have a slope of negative 20 decibels per decade, like so. And let's see, what color can we differentiate here? Let's do this light orange thing. So this is for this term right here. So we're going to be at 0 decibels until we hit 10 to the 3, and then we're going to have a slope of negative 20 decibels per decade. So those are all of our constituent parts. And so now I'm just going to add stuff over point by point. So way over here, I have 0 plus 0 plus 0 plus 0 plus 20 decibels. So it's going to look like 20 decibels, still going to look like 20 decibels, still going to look like 20 decibels, still going to look like 20 decibels. So up until this point, we just have a flat 20 dB. Now, I'm going to have 20 decibels minus this thing that is decreasing, right? So if I look at this point right here, I have 20 decibels plus 0 plus 0 plus 0 plus negative 20. All of that added together is 0, so I should be 0 at this point. And I know that I have a linear decrease, so I'm going to have that guy going on right there. Let's look at what's happening at this point. I have positive 20, positive 20, 0, minus 40. All of those add together to make 0. At this point, I have positive 20, positive 40, so that makes plus 60. I have 0, and then I have a minus 60 here. So that's 20 plus 40 is 60, minus 60, so still 0. Now this guy is starting to increase, so we're going to trend up. And then now effectively these two slopes are going to cancel each other out. And we flat line back out at 20 decibels. So what is this? Fan stop filter. Or not filter. What's our phase angle going to look like? All right, let me, damn it. That line right there corresponds to 10 to the 0. So 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the positive 1, 10 to the positive 2, 10 to the positive 3, 10 to the 4, so forth. Let's make this 45, 90, negative 45, negative 90. All right, so what does the phase response of our constant term look like? Let me go back up so I can remember what color I was using. It looks like orange. So that's literally just a constant term, so it's 0. Then I have that contribution from my first 0, so I was using bright green for that. So I should see that it's 0 until 1/10, and then positive 90 degrees at 10. My other 0 was at S is equal to 100. So at S is equal to 10, it could still be 0. At S is equal to 100, it could be at positive 90 degrees. And that was in light blue. Something like that. Then I have my pole contributions. So at 10 to the minus 2, it should be 0. At 10 to the 0, it should be negative 90. Mine could be prettier, but you guys get the gist of it. And then for my last term, at 10 to the 2, it should be 0. And at 10 to the 4, it should be negative 90. Go. Now I just add all these things together. So I think I used blue. So all of these zeros add together to make 0 until we hit this point. Did I do my, hold on, I might have done one of these. So 10 to the minus 2 is where it starts increasing. Oh, I did that right. Okay. Until we hit this point, then these guys are going to cancel each other out. So this should flatten until we hit this point, at which point, so let's see, right? So here we have 0 plus 0 plus 0 plus 0 plus 0 equals 0. Here we have a whole bunch of zeros and then one negative 45, so that's why it's there. At this point, we have positive 45, negative 90, so that would look like still negative 45. Over here, we have a bunch of zeros, plus 90 and minus 90, so we should be back to 0 at this point. At this point right here, we have positive 45 and negative 90, so that should look like negative 45 degrees again. Oh, but I still have this 90 up here. Okay, so 90 plus 45 minus 90, so these two on the outside cancel each other out, positive 45. No go away thing. At this point right here, these two on the outside have fully canceled each other out. So I have 90 and then I have negative 45. So that's just going to look like positive 45. At this point right here, everything is canceled each other out again. It was where I chose my poles and zeros and the amount of space that I had to draw. So completely and utterly depends on what the transfer function of the system is. Yes.
What happens, I know one example, we got 180, and that's affected the graphic background.
So 180 just means we've completely changed the phase of the signal. So if we have an 180-degree phase shift at a certain frequency, all that means is that at that frequency, if we put a positive signal in, we get a negative signal out. Wrapping all the way back around would require us to have a 360-degree phase shift. So if we were ever, like if we ever had a 4-pole system with no zeros to counterbalance anything, we'd wind up going all the way back around to a 360-degree phase shift. So for this particular circuit, or for this particular transfer function, because we have 2 poles and 2 zeros, we should see that the 2 negative 90s are canceled out with 2 positive 90s at the end of the day, which is exactly what we see. And then I think I mentioned it, but just to be clear, if you ever had repeated poles or anything like that, that would make that transition go instead of 90 degrees to 180 degrees because it's the 2 poles directly added on top of each other. Now, we have stopped here, A, because we're out of time, and B, because to this point, everything that we've covered is real poles. So we're going to kick things off on Friday with what happens if our poles are complex numbers. And that is when we get into resonant circuits. So if we were trying to build a resonator for a specific application kind of. All right, I sincerely hope that this was way less confusing than Monday.